different names all over the world. It can be R&D, it can be R, N and D, R plus D, and especially the European nations call it RDT, that is Research, Development and Technology. So point first, we must understand that why R&D is so important. Why the R&D is a backbone for any nation, any industry, any company, any organization to grow. And why there is so much of investment in R&D which is happening all around the world. But the issues and the challenges are hindering the progress and output, or what we call rate of return on R&D all across the globe. And especially for the nations who have the strategy of convergence or catch-up, refer the yesterday's session, for them it becomes much more important that they synergize their R&D process as per the changing scenario all across the globe and come up with the new paradigms, come up with the new mindset to handle R&D. So is R&D really that important? There are a few points which I am listing here, and let's take them one by one. While innovation is greatly valued, no doubt, that innovation is an engine which drives the economy, and economy leads to higher GDP and then leisure of living and standard of living, and you become into bracket of developed nations. While innovation is greatly valued, there are multitude benefits of investing in R&D. It's not that only innovation's sake we are doing R&D. There are many more benefits. And if you just Google that, what are the importance, benefits of R&D, you will have drop-down lists and you can easily read what are the benefits of R&D. Innovation is one, but enriching technological pool, developing your own capabilities and competencies, understanding technologies, putting science to use. There are immense, numerous benefits why we do R&D. Second, it's essential an investment in, it is an essentially investment for the future capabilities, which is transformed into new products, processes, and services. Very right. That if you want to launch any new product, any new process, any new service, and want to replace your existing list of all these items, then the investment in R&D is an investment for the future capabilities. But always remember, R&D is just merely a tool, and this is really an expensive tool which help you to develop new product, processes, and services. So when it is an expensive tool, then we must have a very streamlined framework that how we are going to handle R&D. I have a data of 2019 where science and R&D spending worldwide totaled around 2 trillion, equivalent to 1.69% of global GDP. So this is hell of a money. A 2 trillion investment in science and R&D worldwide in 2019. Almost 1.7% of GDP is being invested into doing research and development. Earlier, what was happening? The CEOs, CFOs, and CTOs, that is executive officer, finance officers, and technology officers of the companies, they had a mindset, they had a faith that when you were making R&D investments, it is the faith with those knowledge workers and those experts who were sitting in the R&D departments that they are going to use the fund for the good of the organization. And they had the faith in their capabilities that they are going to come up with some new solutions to their current existing glaring problems. But this is not the scenario anymore. They don't have left with that faith because the competitive forces are so high that they want the R&D professionals to run their job and to handle their job much more professionally with a streamlined processes and SOPs. So it's not sufficient just to be innovative. We need some good rubrics. We need some good matrices to show and to signify the effectiveness of R&D. So when the R&D department is taking the funds now, it becomes imperative even for them that they show some kind of matrices and rubrics and some kind of tables which shows and signifies the effectiveness of R&D. Next point is the estimated ROR, on R&D investment is around 30% mean. Sorry. So estimated ROR on R&D investment is around 30% mean and 20 to 25% median. So if you see, if you're investing around 2 trillion into R&D, the rate of return on R&D is just 30%, which is very, very low. So the people and the experts all around are looking for new paradigms, new processes, how this investment ROR can be increased. This is a commercial return. If you talk about the social returns, I have a data of a UK public R&D investment, which is just around 20%. But out of all this, the pharma industry is on the top. Their ROR on R&D investment is very high. So everyone is looking towards now the pharma industries and learn that how they handle their research and development activities. So question is how well you run your R&D. Because this is now becoming a bigger differentiator of your performance against your competitors. It is not that what technology, what product you are launching. So one of the major differentiator now is how well is your R&D managed, how efficient are your R&D processes, how conversant with your R&D professionals are with the emerging challenges all around. So the new era of R&D favors companies who have tight discipline, who have a streamlined process, and who have opportunistic mindset. So this is the reason that R&D is now being looked as an important function within a company, a country, or even globally, because the rate of return is low, investments are high, so we are looking for newer challenges and new processes to handle newer challenges. Just have a glimpse of R&D effort footprint across the globe. So the circles, the bubble diagrams here indicate the amount or the spending you are doing on R&D. So your x-axis is percentage of GDP, and your y-axis is, of course, the money, and the size of bubble indicate the how much you are spending on R&D. So you see the countries like US, China, Germany, Japan, South Korea, even India, they are quite a big bubble. So efficient R&D process is must that how we handle this particular investment and lead into some good beneficial results. Now, countries all over the world, they are putting their expert knowledge workers to work into research departments and the researchers. So this graph shows researchers in R&D per million people. So the investments are high, but here the figures are quite glaring for certain nations. If you see South Korea and Sweden, so they are putting around, South Korea is around 7,000 people per million, Sweden is again 7,000, but you come to India, it is only 215 researchers per million people. And I will come to the data later on that India is one of the nations which has a huge demographic S&T trained manpower. But why it is 215 people per million are involved in research. And from the previous slide, if I see bubble, even India bubble is quite similar to the bubble of South Korea, right? So if I compare India and South Korea, where the South Korea tops with 7,000 people, researchers per million, India is just 215 researchers per billion. So there are certain issues which has to match with the ambition of a nation and the kind of importance you are giving to doing research and development in a nation will decide your global stature. Another set of data which talk about that how the output of R&D is measured and with this output where we stand. So this is a 2019 population versus patents data. So if I see percentage of world population and percentage of patents awarded, and then citizens per patent. So if I see Japan, which is just 2% of the world population, but they have around 46% of the world patents. US is around 5% of the world population. They hold around 30% of the world patents. So if I see the total, that 14% of the world population hold around 94% of the world patents. and rest 86% of the world population just hold 6% of the world patent. So there is something wrong somewhere, that if you have a very high demographic, young, SNT trained manpower, and your percentage of the world population is also high, so what's wrong that your percentage of total patents awarded in the world are low? Why the citizens per patent are less? So these are certain glaring questions, what we are going to see in the presentation, and what can be the solutions for handling this kind of a scenario. So this is a word scenario, but even if I see the BRIC countries, Brazil, 3% of the world population, 0.1% of the patents, Russia, 2%, 0.2%, India is 17% of the world population, just hold 0.3% of the total patents. And China, around 20% of the world population, hold 0.6%. So 42% of world population, just 1.2% of the patents, that is BRICS. So it is more important for these four countries, Brazil, Russia, India, and China, and South Africa also, that data I'm not carrying right now, that those hold around 42% of the world population, what they should do to increase their percentage of world patents so that they have their R&D processes which are much more efficient and effective to lead to some output. And one of the matrices, one of the attribute of the matrices, or one of the parameter of the rubric is that how much patents you have, which is a direct output of doing research and development. So let's understand what is a game of R&D. And then we will see what are the challenges, what are the changes. So first of all, you must understand this is a dynamic game. It is not that you design your procedures, SOPs, processes once, and that is forever. It's going to change as the scenario is going to change. So R&D is a risky but calculated endeavor, like many games of cards. So if you play rummy or a sweep, so you have a calculated moves and you plan your moves a few steps ahead, even the chessboard game. So R&D is a risky but very, very calculated endeavors, like a game of cards. But unlike these games, R&D gives society or a company the advantage with a sizable positive impact. Card games you can play for leisure or a hobby, but R&D you don't do for hobby. Like, I'm not using the taxpayers' money in DRDO to do my hobby, that is research. I'm doing R&D using taxpayers' money so that a sizable positive impact goes to the user. The question what we ask in DRDO is, every money which Government of India spends in buying a defense equipment from abroad, it's a lost opportunity for Indian population, because that taxpayers' money is not being utilized to create road, hospitals, educational institutions, and R&D facilities. Because of these lacunas, that money, which is a hard-earned taxpayers' money, is going outside to buy those equipments. So what is the sizable positive impact of R&D? These kind of questions we ask when we do the evaluation of our R&D efforts. Balancing risk and returns is another trade-off we look into R&D. R&D is also an increasingly globalized endeavor. So today R&D is not localized. R&D is not done in silos. R&D is not done within the same group, within the same organization. The footprint of R&D is increasing globally. What happens with this increased globalized endeavor? Scientists follow the money or the scientific opportunities, basing their operations accordingly. So the scientists, they look for where the money is and where the opportunity is. So all of you work in some kind of R&D institutions or academic institutions. So you will be experiencing that you also look for a kind of a scenario where you can get some kind of funding for the projects. So you write project proposals, you find PIs from your institutions and institutions in India and institutions abroad, so that you can get a money and scientific opportunity, and accordingly you keep on shifting your footprint when doing R&D. So R&D is starved of money, and for when you look for money and opportunities, so you go beyond the boundaries of your organization and even the country. And the international interconnectedness of science is on the rise. So today, any new concept in science which has emerged anywhere in the world, the speed of travel of that concept is very, very high. And that is why the international interconnectedness with all kind of ITC technologies, it is on rise. So cognizant of the innovation and ultimately the economic growth, the consequences of R&D means we all know that R&D leads to innovation, and innovation leads to economic growth. That is well aware, that is a well proven fact. And this is all because of the consequences of R&D. So what governments are doing? So that's why the governments enact policies that affect the investments and commitments in R&D. Because if the R&D is going to impact the economic growth through innovations, so the governments are looking for the policies, procedures, SOPs that how they can make more investments and make the R&D more efficient so that the country's relative scientific and economic standing increase. Today, the demarcation is economic is fine, wealth is fine, but your technological, I gave some examples like technological leader, technological laggards, technological followers, technological parasite. So in the parlance of technology, this is how the categorizations of nations and industries are done. So how the standing improve is also the game of R&D. So dynamic changes and the fusion are redrafting the rudiment R&D processes, because the fusions of so many concepts, philosophies, so many technologies, so many science, so many organizations, mergers, LBOs, and the dynamic changes has forced the people to change their rudiment mindset about R&D. So they are looking for newer ways of handling R&D. And how R&D managers are responding and adapting to the tsunami of changes is what we are going to see in this entire presentation. So R&D manager, the role of R&D manager has changed today. A R&D manager of yesteryear was sitting on his comfortable chair in the ivory towers and was doing R&D in the silos. But today, the R&D manager is outside. He's an extrovert. He's integrator. He is a facilitator, so that he can bring the competencies into that tower, and they are able to adapt and to handle the changes. The force of change is very, very high. So we always call a tsunami of changes, which is high. So this is a dynamic game of R&D because of these changes. And very fast response and adaptation to these changes make this game very, very tiring. So what is the game of R&D? Who are the teams? Who are the players? What is the arena and what the stakes? So game is, it's a highly risky game, but very rewarding. That's why that attracts so many players. So if you succeed, the rewards are very high. And that's why so many players are lured into this game of doing R&D. Teams are ambitious business firms, organizations, and nations. So the organizations which have an ambition to lead in technology, the nations who have an ambition to be a developed nation because of technologies. So these are the teams who play this game. Players are scientists, researchers, designers, engineers, marketing people, legal people, politicians, bureaucrats. This list is unending. Can you please mute your mic? There's a bit of disturbance this side. Right, so list is unending. All stakeholders which matter and which are required, they become the player to this game. Arena is value, newness, technology intensity. So these are the arenas which create the niche or a competitive advantage or a USP. So what is a new value? What is a newness? What is the intensity? Whether my technology is a developed technology, new technology, old technology, high technology, mid technology, appropriate. So there's so many terminologies which we can use to define the arenas. And stakes. Stakes are winners take all and losers become extinct. So this is the kind of stakes is being added into this particular game. So if you win into this game, rewards are very high. But if you lose, you can also become extinct. So this is what we call the game of technology. And because of rewarding, so many players jump to it. But number of people become extinct because they lose, and they lose everything. and the winners take all. This is the kind of reward system into the R&D game. If this is the game of R&D, then what are the different types of R&D? First is a basic research. We all understand. A basic research is fundamental research or a curiosity-oriented research, right? So either you are trying to prove some basic concepts, you are talking on the fundamentals, you are doing some research in physics, chemistry, mathematics, life sciences, biology, botany, to establish some fundamental concepts, to come up with new theories. It's a fundamental research. And it can also be a curiosity-oriented research, right? So if I want to do the research in the area of nanotechnology, right? So this is a kind of curiosity-oriented research. If I am doing a research into, let's say, extraterrestrial or below sea, deep sea, they're all a curiosity-oriented research. Then there can be a strategic research, which is also basic, that we must find some kind of a electricity storage technology so that the size of battery is less and the storage capacity is very high. So it's a very, very basic research. And that's the research is going. And if you see that in any equipment, electronic equipment or electronic equipment which is portable, it is limited. The limiting factor is the size of battery and the storage capacity. In the cell phones, as the apps are increasing, as the display pixels are increasing in the display screen, the battery consumption is more. So that's the strategic research going on in the area of basic, that how we can devise new kind of technology where the storage capacity is more and the size and weight is less. So there's a strategic research. Second category can be a directed basic or exploratory research. So all S&T projects, especially with reference to DRDO, my science and technology project are directed basic. So we have a problem, and to solve that problem, I have taken science and technology basic research, but this is directed to solve that problem. I am making a lighter, smarter, and very tough materials. I'm looking for a plasma material which is transparent, but the strength is of steel. So this is a requirement in future, and the directed basic S&T project is towards that. So my directed basic and exploratory research are into this category, that first we foresee a problem and a requirement in future, and then we work backward, use basic research, but we call it a directed basic or exploratory research. It is different from fundamental and curiosity and strategic, because fundamental and curiosity may not be directed by the end result. A strategic research may not be directed by the end result, but we are doing it, that sometime in future, this may prove my trump card, right? But directed basic and exploratory research is based on the end result and the end need. So that's why they are called directed basic and exploratory, and we do it with the S&T projects. My next category is applied research. Now, if something which comes out from the basic research, or if something comes out of the directed basic or exploratory research, now how to use that research output into some useful application? Then we call it applied research, like a mission-oriented applied research, technology development, and problem-oriented research, that is again applied research. Now, all countries are working so hard to find the vaccine for COVID-19. The countries are making so many technologies how to fight this pandemic. So this is the applied research of basic and directed basic, but it is problem-oriented. So this is what we call as a problem-oriented research. And the mission-oriented applied research is that this nation has taken up a program that we will make 175 gigawatt of clean energy. So that mission, that is a clean energy mission of India. So all my work of research, which is happening under clean energy initiative of India of 175 gigawatts of energy, that all is categorized under applied research. And here we do technology development. Then, when the output from applied research is mature, when the applied research has shown the potential that this particular technology developed is useful, then I have to do a research which is industry-oriented research, so that I can make that product into numbers and it can be disseminated to the society for the benefit. So my experimental research, my proto development research, my product development research, and subsequently product improvement research. This comes under industry oriented research. So my CSIR, that is an industry oriented department. So that is, they take the input of basic research, directed basic and applied research from all other organizations and do very specific industry oriented research. And the last category is, now applied research and focused is a customer centric output that you must understand. And then the last I put directionless research, no end use. And I'm very sorry to say that the number of university research scholars who are either doing research for their MTech dissertation or PhD, that is a directionless research. Why I'm calling it as directionless? Because if I see the data and comparison, that how many of PhD theses in US and China get converted into patents is very, very high, nowhere near to how many of PhD theses in India get converted into patent. There is no match at all. So that's why I'm saying it's totally a directionless research done with the aim just to get a degree, not to help nation to develop their technological pool, scientific pool, or capability pool. So unless we tap this segment of research and weave it and synergize into the national technology strategy, India is going to be always a laggard in technology or a parasite in technology. Because if I study the systems of doing academic research in those nations, they are directed by either applied or industry oriented or at least extrapolatory or a strategic research. Because most of these programs are funded by the organizations which are into a customer centric output mindset. So they drive or they pull out of research initiatives from these universities which are going to be linked either to a strategy or to some kind of customer-centric output. But in our scenario, whether we take Indian Institute of Science or IITs, their linkages of their research with the industry is a big, big question mark and is a big requirement to be changed. So that's why I put it as a directionless research with no end use. That is a university research scholars, what we do in India. Now, for doing this research, what was the classical paradigm? Right. So what was the thinking earlier? How the research labs of the yesteryears used to work? I would like to mention here that the research labs almost all over the world have roots in the great labs of pre-World War II. So World War I and World War II has forced nations to do immense investments into their research activities. But that kind of research was only limited to defense application. And later on, all the research which was done for defense application during 1930s, 40s, till mid-40s and even late 40s, that was commercialized to commercial market to recoup the money they have invested into the research. So most of the research labs, they have their roots in pre-World War II. So that's why the philosophy and the mindset of doing research is based on a big word that is called confidentiality or secrecy. So the research means secret, develop means secret, technology means secret. So this was the mindset when we started our great research labs of pre-World War II. What was the syndromes at that time? So discovery and invention, which was happening in those kinds of labs, they suffered from NIH syndromes. NIH stands for not invented here. So means those nations were not using any kind of a technology which was not invented in the research labs of their own nations. So that's why if you see Russia, you see China, you see NATO, you see US, they are still have this kind of syndromes that they will never use a product which is not invented within their own country or within their own labs. So NIH syndrome is still a very, very important syndrome which is hampering or stopping the R&D processes to change and R&D paradigm to shift. Now the R&D people, or the scientists or the researchers or the knowledge workers who were working in this pre-World War II laboratories, they considered themselves as the custodians of future. They thought that they are the most knowledgeable, they are the most intelligent and a genius set of individuals or group. So they will dictate what will be the future of technology in the market. What will be the growth of technology in the future, and what will be the products based on technology in the future. So they never considered the ultimate user or a customer equivalent to them in terms of geniusity or in terms of the intelligence. So they said whatever we are going to give them in terms of technology, they will be happy with that. So custodian of the future is the kind of mindset. And even today, number of laboratories who are doing R&D suffer from this syndrome, that the people who work in R&D, they think they are the custodians of future. They are know all, and they are the people who are going to make technology and customer is going to accept it. So those labs were very underfunded. And that was like a common fact. There was no money available because the World War I, World War II led to a great economic depressions. So the money was not available. Because the money was not available, so the mindset or the propaganda was that they are doing very much secret work. And without this secret work, which is of very high-tech nature, the nations are going to tumble, they cannot able to win war, and their economy is going to suffer. So these are the kind of propaganda these research labs were using to get funds, but they were very much underfunded. Those R&D labs always remained autonomous. They said because we are custodians of future, we shouldn't be controlled by any other strategy of the organization or a corporate. So they remained autonomous R&D labs. So autonomy to R&D is the concept or a pre-World War II, but this is not the scenario today. We will see what are the changes happening. And in this category of lab, the dominance was from the Occidental countries. So Europe and US, they were dominating this kind of laboratories and this kind of a culture, mindset, and processes of doing R&D. Power was fundamental. So they were custodians of future. They were the holders of information and knowledge. They were protecting everything under secrecy. And because they thought that they have the knowledge and information, they have the power. So that is the fundamental mindset of doing R&D during that era. Time was ignored. Technology was simpler. There was no concept of time. They can take decades and decades for doing technology development or doing R&D. That was not stringent frameworks for time that you have to complete this R&D job within a given time. And that time, the technology was also simpler. Products had very few technologies in that. There was no amalgamation of technology. There is no cross-transplantation of technologies from one stream to other stream. So the job was simpler, so they were able to handle it. Protection was through secrecy. I have explained that. And this led to what? This led to a never-ending chess game between two nations, two poles of power, US and Russia, and what we call it an era of Cold War. In fact, if you work back, the era of Cold War was just the secret R&D labs two were doing. You all know the race of launching first space vehicle, race of launching one satellite, race of that which nation will put the foot first time on the moon. So that kind of a secret work was going in space. That kind of secret work was going in defense. And later on, the work of these Cold War era research labs commercialized after this Cold War era over in 1990s. So this kind of classic paradigm of doing R&D just led to an era of total disconnect between two poles, and both were developing simultaneously into different parts of the globe. And this was a never-ending chess game which was happening. So this was the classical paradigm of doing R&D. Now let's see what are the changes which has happened and which has led to transforming the R&D, how we do it today. So kaleidoscopic changes. Why I call it kaleidoscopic? Because they all interact with each other, and then this interaction of all these changes tell us that what kind of R&D scenario we are placed in today. So first change is shift from information to knowledge. If you see here, power was fundamental. Power was fundamental because they were the custodians of information. Information they were holding, they were not making this information travel outside the R&D labs, and this information was giving them the power. But there was a shift somewhere in mid-1990s from information to knowledge. You all know there is a term called information economy, and now we calling it as a knowledge economy. So what's a change? I'm not going into that deliberation because that itself is going to take time. But this shift from information to knowledge led to some kaleidoscopic changes how R&D is being done. But just to give you example, what's the difference between information and knowledge? Information is mostly the published data. So my railway timetable is an information. But how the Indian railway trains operate, whether they are on time, they are delayed, and all kind of experience I have about that information becomes my knowledge. So knowledge make me use this information for the good. So as the information changed to knowledge, the way of doing R&D also changed. Shift from training and development to learning. Earlier, there was a concept that, especially the knowledge workers, they can be trained and developed. So the scientists, researchers, they can be trained and developed. No, but today the concept is they will be self-learning. There will be a learning curve. There will be a learning growth. And there will be some kind of a learning by working in the system. So training and development was the era which was before 1990s, and the learning is the era later on. Shift from bureaucracies to networks. The older R&D labs were very, very bureaucratic because for maintaining secrecy, hierarchy, and mostly working with defense, the bureaucracies also seeped in into the structures of R&D. But today the scenario is R&D doesn't work on bureaucracy. So always I tell, because my defense research and development organization is part of defense, so much of bureaucracy is in doing R&D. Nowhere in the world, any emerging technology R&D labs work with bureaucracies. Even DARPA is not part of DoD, Department of Defense. That is an independent department. So take DRDO out of Ministry of Defense, make them autonomous, break the bureaucracies, work towards networks. This is the way to solve the problems we face. So bureaucracy is not for R&D, networks is for R&D. So this is another change we are seeing in R&D setups today. Shift from specialized discipline to supra-functional aggregation. Today, R&D is not a single specialized discipline. In fact, it is a supra-functional aggregation of so many disciplines together. So how and why we cannot bring the supra-functional aggregation from all across the competencies in the nation into a common platform to do R&D? Imagine a platform team where I have a facility and some kind of processes and some kind of procedures. I can bring and pull the people from academia, from industry, private sector, from R&D labs, even the experts abroad come and work for me doing specialized R&D. So supra-functional aggregation is a term we use in R&D today. Shift from local national to transnational. Today, no nation do R&D in silos. Even the topmost secret programs of the world are transnational. The most complex combat aircraft, F-35, that is a Panther of US, is a combined program of 15 nations, 15 nations together. So gone are the days when the programs, even of this secrecy and complexity, are done locally within the nation. They are transnational programs. So R&D labs have to open up, go beyond the borders of the nation, get the competencies. And you'll be surprised to know that 7% of F-35 Panther, most complex aircraft of the world, is made in India, in Ludhiana. 7% components goes from India. So this is what is called transnational doing R&D in kaleidoscopic changes. Shift from competitive to collaborative strategy. Today in R&D, there is no competition. That's why bigger companies, DuPont and Merck, HP and Canon, Nike and Adidas and Reebok. So these are the giants who were the competitors earlier. They are collaborating together to make new kind of products and technologies. So competition is gone, collaboration is in. worldwide virtual R&D environment with vertical integration of competencies. Today, the concept is the R&D is done not in the physical environment, it is done virtually. I'll give some examples. That how virtually R&D is done. We all know there is an aircraft called 787 Dreamliner. So entire Dreamliner was designed, developed, tested in a simulated environment, fabricated, assembled, and went for the first flight straight in 5 years. Where the earlier aircraft design, development, and the complete cycle was taking 8 to 9 years. How they were able to save 4 years straight? It's a virtual R&D environment. So teams were working across the timelines. So when the team in Japan and China were sleeping, the US and the Europe was working. And when they were sleeping, the entire bundle of the design and R&D was coming to the Orient countries, that is the eastern side. So just by shifting these packets of design from left to right or east to west, they were able to manage and do the entire R&D in straight 5 years, cutting down 4 years. So this is what the virtual R&D environment today we are talking about. This is how the entire R&D of automobile sector is done in Chennai. You name the best automobile company in the world, they have their R&D facility in Chennai. Whether it's a BMW, whether it's a Mercedes, where it is Volkswagen, you name the company, R&D sits in Chennai. They all work in virtual R&D environment. So this is the change they have adopted. Then value addition through open sourcing. We have all heard of this term, crowdsourcing. We have heard the term open innovations. What are these things? So value addition through open sourcing. And whenever I talk about crowdsourcing and open sourcing or open innovation, the question comes to DRDO is, when your technologies are so secret, how you can do open sourcing? And I can cite you 10 examples that the latest versions of submarines, latest versions of frigates, latest versions of ships, latest version of small weapons, their problems are all solved in open source. Their problem is all put on the open source and the people give their comment how to improve it. F-35 entire design is available on the internet. Any person can go to their website of Boeing and Lockheed and give their comments how to improve the design. So that is how they are open sourcing the value into their R&D, and where we do and how we do, where we stand in this. Intellectual capital and property, your sanctity of the patents is a question mark. So if everything is being open sourced, everything is under collaboration, everything is under transnational, is a supra-functional aggregation, then how to protect the capital, intellectual capital? What about the patents? So the question is whether the sanctity of the patents, whether the value of the patents is going to hold in future. And I would like to mention here that I was attending a think tank meeting in Washington, and they said that after 2030, there will be no patent, there will be no concepts of intellectual patents. And to prove this, the speaker was from Tesla, the person who works for Elon Musk. He said in 2014, all the patents of Tesla are available in open domain for anyone to copy and replicate the product. They are saying we are not protecting any of the technologies of Tesla because unless we make the patents open, we will not encourage the healthy competition. So this is the concept of a company, Tesla, which is in the forefront of doing R&D. And we want to protect everything with the intellectual capital. With this kaleidoscopic changing, you just note down in your notebooks that by 2030, the concepts of patents will just vaporize. There will be no concept of intellectual property protection because the companies who work in this direction are already done it. So all Tesla patents, even their lithium-ion battery patent is in open. It's a challenge by this company to the competitors that if you have capabilities, replicate it. So this is how they are doing the R&D of future, and this is how the changes are forcing R&D to change in future. So with this changes, this is how the R&D has shifted over the years. So 1950s, Immediately after the recession of World War was over, R&D still was based on the secrecy of laboratories, and it was individualistic effort. It was individually based on individual creativity, and scientific inventions were happening, and we call it first generation of R&D. Their individuals mattered, and the individual were doing the job. So the person who holds the maximum number of patents is Edison, has around 175 patents. Is the individual created laboratory. So his Edison labs in Princeton, and that laboratory was making so much of research and taking so much of patents. So first generation of R&D. Now 70s, we saw the first shift, where from individual, the R&D became establishment level, right? So you shifted from doing as individual to establishment level, and your R&D became a multidisciplinary, and you shifted from making small technologies to systems. So when you changed to system development, naturally it became the responsibility of the entire establishment, and the second generation R&D development started. And I would like to mention here the first project which was handled using this concept was a automobile car by Ford, which was model was a Taurus. So Ford Taurus told the world that how the second generation of R&D is being done, where the entire establishment is involved. Now 80s, from establishment, you shifted to corporate level. So your centralized R&D projects, linking R&D to corporate goals. So here you started synergizing business strategy with R&D strategy, and we call it as a third generation of R&D. But even up to this level, your R&D was within the corporate, your R&D was within the nation. But 1990s, we came to know that there's a new trend of doing R&D that is global level. So now you are shifting from a nation corporate level to nation level to global level. So knowledge integration, management of internal and external knowledge, and we call it the fourth generation of R&D. And then beyond 2000, 21st century, your R&D became a networked level R&D. And I gave the example of Dreamliner 787 aircraft. There's a first aircraft which took the leap into doing next generation of R&D, and they did network level R&D. So they designed concurrent design facilities, CDFs we call it, global innovation infrastructure. They created knowledge channels, and we call it the fifth generation of R&D, and how we do R&D at the network level, where the entire globe is involved into doing the job. So we will see all this into detail and see that what is the learning for us for doing research and development. So first generation, which was from 30s to 60s. So when I say 30s to 60s, means is a World War era, World War I and World War II. So R&D in the ivory tower, no intra and inter-functional communication, no link with business strategy. R&D was always considered as an overhead cost, and dominance was technology push. So this was the scenario. And to put it here, there are a number of laboratories, even now in 2020, they work in this kind of a mindset. So this is the first generation of R&D. My second generation of R&D, business units are customers. So now you are becoming customer-centric. Beginning of R&D management concept. Because your cost, your money for R&D and the time was becoming stringent, so the R&D management concept came. So somewhere in 1973 and 74 came the first publication, international publication on R&D management. A sense of market orientation. However, even at this stage, there is no aggregate view, no prioritization of projects within the business, across business or organization. So this is the transition phase. You were shifting from first generation to second generation, the major change which happening, that now you are looking outwards towards the market orientation and customer orientation. This is the second generation of R&D. So what kind of models we were using? My first generation was basic science to design engineering, to manufacturing, to marketing, to sales, all sequential. But the second generation, the slight change happened, that from basic science, we shifted to market needs, market orientation. So market needs to development to manufacturing to sale, even this remains sequential, right? So you can refer to this paper by Rothwell, and this paper came in 16 that gave the different generations of R&D to detail. So only change which happened that you shifted from the internal orientation to external, but external was only market. There was no aggregation of other facilities. Third generation was Attention to cross-project, cross-business synergies. Now you are looking at that how the R&D, different R&D labs are working and how you can synergize across businesses and across R&D projects. So came the concept of portfolio. That what kind of different R&D management portfolio, R&D portfolios, and how the R&D portfolios can interact with each other to come up with a newness. So integration of R&D strategy with the business strategy, and came the concept of technology push and demand pull. That there has to be some kind of a technology newness, but also there has to be some unmet need. Only then your R&D come out. So the model which is Rothwell gave in 1994, that for generating ideas, you have a demand pull and you have a technology push. Now, demand pull and technology push create ideas for the R&D teams, and then they do research, prototyping, manufacturing, marketing, and marketplace. And this is supported by the needs of society and the market and state-of-art technology and production. These are enablers. These are the pullers, facilitators, and this is the kind of model, a combined coupled model. This is the third generation of R&D, how we do it. But the change is now you have an orientation of market. You have a synergizing the R&D portfolios. You are working across the businesses, across the R&D labs, and generating ideas. So you see the slight change that how R&D is being done. Now, fourth generation is you shifted to knowledge economy, 1995, 1996. So management of knowledge from diverse sources. Concurrent learning with the customer. So now the major shift happened that the R&D people realized that even customer and users are knowledgeable. Customers and users can also lead to developing new concepts in R&D. So they started concurrent learning with the customer. So cross-disciplinary and cross-organizational teams, management of technology in the form of IP starters, a concept of, because now this knowledge, information you can put under lock and key and you can hold information and you can say, because I have information, I have power. But how to protect the knowledge? Knowledge in the form of technology. So came intellectual property patents. So this concept came. So now the R&D people were going out of their R&D labs. They were sitting with the users and customers, trying to learn and capture their knowledge and work backward to do R&D. This is the fourth generation of R&D. And the fifth generation is on the collaborative R&D, where you involve all stakeholders. You involve suppliers, you involve partners, customers, distributors, and stakeholders. They said customer is fine, but you should integrate your forward integration and backward integration. Complete chain, complete pipeline has to be integrated because they also have some knowledge. So cooperative system of doing R&D started where backward integration and forward integration, right from suppliers to distributors, brought into the common platform for doing R&D. And cross-boundary knowledge flows and learning. So this cross-boundary, because your suppliers were outside the organization, your distributors were outside the organization. So this cross-boundary knowledge learning helped to do us the fifth generation of R&D. And electronification of innovations, liberal use of IT tools started. So that's why when I told you about the fifth generation, I mentioned there is a term called concurrent design facilities, CDFs. So just Google it and see what the CDFs are. Liberal use of IT to do the electronification of innovation. This is what happened in fifth generation of R&D. So from first generation to fifth generation, how the role of a R&D professional changed. Classical R&D professional. So this professional was either a chemist or a physicist or a biologist or a mathematician, all working separately in silos. Or he was an electronic scientist or a material scientist or select few engineers or academicians. This was the classic R&D professional. But what is a 21st century R&D professional? Or a technology developer? He's a strategic planner. He's a visionary. He's an entrepreneur. He's an internationalist. He's a persuader. He's a networker, supra-functional aggregator. He has a quality, cost, and time consciousness. And that R&D professional is a knowledge innovator. So see the change. Kind of competencies you require to become an R&D professional has totally changed. We don't need us individual experts in our domain areas. We want who is able to integrate supra-functional integration, who can persuade, who has entrepreneur skill, who has a vision, who can make a strategy, and who has a quality, cost, and time consciousness, that is a customer centricness, he is an R&D professional in 21st century. So that's how the paradigm from first generation to fifth generation and change in the requirements of R&D professional happened all across the globe. Now, with this fifth generation, what are the models of doing R&D? What are the approaches the R&D institutions follow for taking their concept in the laboratory to our technology in the land? So lab to land approaches, what are there in the 21st century, a fifth generation of R&D? So there are three popular approaches. These three popular approaches are integrator, orchestrator, or a licenser. So we have R&D professionals, we don't call them the R&D people. We call them either they are the integrator, or they are the orchestrator, or they are the licensors for doing R&D. And what are their jobs? Their jobs are, so what they do, manage all the steps necessary to generate profits from an idea. So it's an integrator. What orchestrator do? Focus on certain steps, link with partner to carry out the rest. And licensor, license the innovation to another company to take to the market. So see, integrator is managing all these steps for doing R&D in-house. Orchestra only focusing on certain steps, and licensor is just like a middleman. He take our R&D input from one R&D lab, give it to the other institution which has a competency in the downstream, and he do the job. So this is how the R&D gambit of doing R&D has changed. So investment requirements are very high if you are an integrator, and if you are an orchestra, medium. If you have a licensor, low. So depending on how you chart your technology strategy, you have to find the competent manpower either to be an integrator or an orchestrator or a licensor to be available with you in your R&D labs. If you want to establish a technology leadership, means all the steps you want to manage in-house, you must have integrators in your lab. But if you are not a technology leader, you are just doing a certain portions of that, then you don't require the complete team. You only have the people with this kind of skills. And then to licenses. What are the capabilities required? All are listed here. So like a strong cross-functional links within the organization. He must be expert in product design. He must know about the manufacturing process because all steps are done in-house. He must know how to source the technical talent, and he also understands the strong market position. So means all skills required from the upstream to downstream integrator must have, or he must create a team which have all the skills. That's why the investments are high. And when they are used, this kind of a skill, when the speed to market is not critical, but the technology leadership is crucial. When the market customer tastes are stable, when the innovation is incremental. So this is depending on the what kind of job you are handling, you decide that what kind of skills must R&D professional possess. So I'll not go into this detail. You can always refer to the paper I am mentioning here, Innovating for Cash, Harvard Business Review 2008. And this is by NGU and Sirkin. And you can find the details of all this paradigm shifts and how the integrator, orchestra, and licensor are doing their jobs in an R&D environment. Now, 5 generations are okay. Now, what is beyond? Are the R&D changes in the environment are now stagnant? Nothing is happening. I was talking about 2000 or 2005. Now we are in 2020. So what has happened beyond that, which very few authors are able to capture into their literature? But some kind of insight I want to provide you here. That the sixth generation, a paradigm shift in R&D process. Now, what is the sixth generation? Conventional linear innovation model no longer works. So conventional linear model is first you generate idea, then you do some R&D, make technology, make prototype, manufacture it, and then sell. Is a linear model, right? So this linear innovation model no longer works. Reason is the times are very, very short. The movement of the expert manpower is very frequent. Today, the knowledge workers have a global footprint, and there is so much of cross-functional aggregation is happening. across the borders of the nation and the industry. So there is no time that we take everything sequentially and we follow the linear innovation model, which is conventional, right? So there are changes in the relationship between basic science and engineering and technology. How the basic science, engineering, and technology used to interact earlier, and how it is happening today with so much of simulation all around, so much of simulation capabilities, it has changed. And the advent of knowledge society and knowledge network has led to an era of open innovation. All of us have heard this term open innovation. So let's see what is open innovation and what the open innovation tell us, that what is the sixth generation of doing R&D. Open innovation is a term used to promote a knowledge age mindset towards innovation that runs counter to secrecy and silo mentality. Like a World War II and the later R&D labs with a secrecy and silo mentality, the open innovation is dramatically opposite to that. It promotes that knowledge lies everywhere, so you should go outside and capture that knowledge. So in the world of widely distributed knowledge, organizations cannot afford to rely entirely on their own research capabilities. So open innovation was defined as the use of purposive inflows and outflows of knowledge to accelerate internal innovation and expand the market. So this is just a definition. That how you use inflow and outflow of the purposeful knowledge, and then create a system that you innovate sitting in open with everyone instead of sitting in the controlled environment within your organization. So earlier conventional model was that you do basic research to production, and that's how your ideas goes in a sequential model, and then you have so much of iteration, and these iteration used to waste so much of time. So this conventional funnel approach is not going to work. So the model today is that you have an internal technology base, you have external technology base. You capture this internal and external technology base into the funnel that is your organization, and then you use internal technology sources. External technology sources means out licensing and in licensing, and then create our technology with other firms and market, create new markets and address the current market. So this is the kind of a framework we used in open innovation. So closed innovation companies operate under a self-contained innovative environment, whereas open innovation companies source external knowledge for their innovative management strategies. So there are new management strategies which are very innovative, which are telling us that we must now open up and use the external competencies available, capabilities and competencies available to source it inside to make innovations happen. So this is a 3M model. 3M model, they take ideas and innovations from inside and patents and innovations from outside. They bring it in and then they churn it through their process to address the current market and create new market. They use a term inbound open innovation, outbound innovation, coupled innovation. Inbound means that you are getting the ideas from outside, matching it with your competencies and creating the innovations within the organization 3M. Outbound, they are taking the capabilities of 3M outside and using the platforms available outside the organization and doing outbound innovation. So they have 68 R&D labs all over the world. Headquarters is in Minnesota. And then 68 labs use inbound, outbound, and coupled innovation models to generate new technologies. At what rate? You will not be able to imagine. 3M worldwide launches one product, new product, almost every day. Within 24 hours, a new 3M product comes. And they say that there is no human in this planet, on this planet, which is not using a 3M product. Today, most of us are using the masks, which is a technology from 3M. Even all of us use an automobile. Every automobile has almost 2% of components which are from 3M. 3M is a company. This is the only company whose products have gone extraterrestrial. They have landed on the moon and come back. So this company has a capability of launching one new product every day. Go to the website, learn the practices, innovative practices of 3M, because inbound, outbound, and coupled innovation is there right now. At this time, That is their base of doing new innovations. Fine, sixth generation is also okay. We have seen that few companies have adopted the open innovation models. We may be, in India, may be far behind, but the world has changed and adopted to the open innovation models. So now let's see what is beyond sixth generation. Now, these companies who have mastered open innovation, what they are looking at. So I always tell you that whenever you find a time, just go through this book, Thomas Friedman's The Word is Flat. Excellent book. That will just open your minds, open your eyes that how the world has changed and where we are placed and how rudiment we are into our thinking and in our capabilities of doing the R&D. So today's globalized world is being flat. This is what the author says. So one cannot deliberate on innovation without addressing the paradox of globalization. When you're talking so much of globalization, how can you have a R&D lab in your nation with a mindset of self-reliance? That is absurd. That is a mindset of 90s if you talk of self-reliance today in your nation. So today nothing is called self-reliance because there is a globalization and R&D has also become globalized. Innovation is certainly occurring globally. So globalization, F-35, I gave the example earlier. This country, Boeing and Lockheed, has a capability of making the entire aircraft. But you'll be surprised, only 3% of F-35 is made in US, 97% is outsourced globally. So this is a globalization of R&D. And word is flat, this kind of organization concept they're talking about. Innovation is certainly occurring globally. It occurs in Silicon Valley, Shanghai, Bangalore, and Tel Aviv, and they are all connected. Right, business process outsourcing has transformed US economy as well as the places like Bangalore in India and Dalian in China. Gone are the days when India was doing BPOs, when India was doing the call centers. Today we are a nation who are doing KPO, knowledge process outsourcing. Knowledge process outsourcing means outsourcing of R&D activities that has come to India. The paradox of this global economy is that more we witness the forces of globalization through ICT, that is information and communication technologies, more we realize that innovative is being localized in few areas and that we call hotspots. And today hotspots are Bangalore, Hyderabad, Tel Aviv, Dalian, Silicon Valley. These are the hotspots where the new innovation and R&D is happening. So in knowledge economy, what is happening? Every hotspot is leveraging the regional entrepreneur skills. So the entrepreneur skills in India are different, entrepreneur skills in Tel Aviv are different, and entrepreneur skills in China are different. So they are using this globalized knowledge economy, but leveraging their localized entrepreneur skills to create new values. So India entrepreneur skills are doing frugal innovation, frugal R&D. R&D in the low resource setting. So any kind of R&D which is coming to India, the USP is a frugality. So that is the local entrepreneur skills, and the globalized knowledge economy is what we call a word being flat. So need of the day is to connect these hotspots. How can we connect these hotspots and take a model, make a model of doing R&D and establish a global knowledge channel and construct an innovation superhighway? So beyond sixth generation is how can I construct an innovation superhighway, global innovation challenge, so that these hotspots are connected and the R&D is done between these few hotspots. So the model which China uses is called QSO, collaborative innovation. And they promote the harmony within the partners for doing innovation. So R&D Collaborative Innovation Center of Shanghai, which is a model beyond sixth generation, the space for collaborative activity. Researchers in China use this facility to meet with many other researchers around the globe to conduct global R&D. All together, different perspective and mindset to manage R&D process. This is sixth generation and beyond, and this country has able to master it. R&D Collaborative Center, Shanghai, they call it QSO is their name, and the promotion, what they do, the mindset of doing is that is harmony. So this is creating an innovation superhighway, how Shanghai, Tel Aviv, Silicon Valley, all hotspots have been connected and they are encashing the global innovation challenge to do the next version of R&D that is beyond 6th generation. We in India don't even think in this direction. So what's the change? Open innovation, traditional syndrome was NIH. Next syndrome is PFE, proudly found elsewhere. So they are not saying that new R&D is done where we are. They are saying proudly we have found it elsewhere. So the next open innovation acronym or the syndrome is PFE. Market orientation is technology push traditionally. Now it is a market push. Development was wide portfolios. They are doing only in focus portfolios. Transparency, R&D intensity, but today that transparency is R&D efficiency and effectiveness. And their rubric is based on total factor productivity, TPF. Agile and frugality, R&D was wealthy. Now we are talking on ROR on R&D, return or rate of return. Globally connection, centralized footprint, global innovation network. Collaboration, organization silos, we are working in jelly teams, cross-functional platform teams and jelly teams. Virtual development, physical prototyping, today we are talking about simulation and rapid prototyping. Focus, scientific and technical, here focus is 2D and product engineering. So the next generation R&D, which is beyond 6, this is the factors and attributes we have to look into. So with this brief on paradigm shift, let's run through very quickly what is the STI landscape in India. Right, I'll take another 5-6 minutes to finish that, and then I'll take questions and your doubts. So what is the STI landscape in India? And then you will be able to have some kind of a sense of gap which exists between the R&D infrastructure and philosophy and processes in India vis-a-vis 6th generation and beyond, which other nations are already adapting to. So changing, we had our first scientific policy in 1958, and now we have our science and technology innovation policy of 2013. And the aim of this policy is accessibility, affordability, diffusibility, and sustainability, right? So Indian society as a major stakeholder, we are doing R&D for Indian society, and the aim is inclusive growth. And now 2020, we are coming with a new draft of STI policy, that is DST is doing it under Professor Vijay Raghavan as the chairman, who is the principal scientific advisor to PM. Now the footprint of Indian R&D is this. We advented into the era of high-tech system developments or doing high-tech R&D somewhere is 1979. And this is my roadmap, which is made by the Department of Science and Technology, that this is a roadmap that how Indian technologies are nurturing by 2020 I've given. And this also has projection up to 2030. And on the top, we have space and defense technologies, and bottom, we have the civil use technologies. So you have a passenger aircraft, you have a hyperplane. And if you remember, just a week back, DRDO did a test trial of a hypersonic technology development vehicle. So 2020, and this is how it is being mapped year by year. And this is the S&T landscape, what I call for India. Now, who are the organizations which are involved in doing S&T? So we have a government and S&T department. We have independent research institutes. We have in-house R&D of the private companies. We have some NGOs doing R&D. We have a state governments doing R&D. And we have a central socio-economic ministries doing R&D. So you have a Department of Science and Technology, Atomic Energy, Biotechnology, Earth Sciences, Agriculture Research, your CSIR, your DSIR, CSIR, Medical Research, DRDO, Space, and so on. These are the central government S&T departments. Why I'm focusing on central government? Because maximum funding and the percentage into R&D in India is done by the central and the central departments, not by the private and the state departments. So this is a setup. You have a council of ministers on the top. Then you have a principal scientific advisor. Then you have a prime minister who is guided by a Niti Aayog and a scientific advisor. Also, you have a member of CIE, FICCI, and industry consortia advising. Then you have all these departments, HRD, E&F, HMF, your computer and IT, MITI, Earth Sciences, S&T, Department of Defense and Agriculture. And under this, you have all these departments. And this is my workhorse, with all the laboratories doing R&D. Like DRDO have around 50 labs, DST has around 28 labs, DSIR has n number of labs, biotechnology has labs. All these laboratories fall under this kind of a tree to do research and development in India. I can skip this because time is limited. Now, the central sector.
He is on Indian Embassy in Germany.
Now, the central sector put around 59% of fund for doing R&D. State is only doing 7%. Private sector is doing around 30%, and higher education is just 4%. So, major chunk of doing R&D in India is limited to central sector. And if I take the central sector department-wise, DRDO consume around 32% of R&D budget in India. Atomic energy take 14%. CSIR take around 10%. And Department of Space, where is that? Department of Space take around 15% of defense budget. So if you see DRDO, Space, Atomic Energy, CSIR, these three major departments make a major chunk of doing research and development in India. Whereas the private sector is just 30%, state and higher education is very minimal. So this 4% and 7% chunk and 30% has to be mobilized if we want to become a serious nation in developing technology. The weakest link in doing R&D in India is the higher education sector. That is just 4%. So that's why my term directionless research in the beginning proves here that just 4% contribution in doing research by higher education, where in other nations it is totally drastically opposite. And this is the output consumed by number of industries. So maximum R&D effort done by the central sector is consumed by pharmaceutical and healthcare, 22%. 14% by technology and services. And if you see, another major sector is automobile, which consumes around 7% of the funding. And this is the industry-wise consumption of R&D effort by Indian R&D centers, which is mostly central, and how this is being utilized by different industries and cluster you can see, and the percentage you can see. And if I see the activity-wise, applied research consume around 41%, experimental development consumes around 34%, basic research consume only 17%, and other activities 6%. Reason? Because DRDO, space, atomic energy, CSIR, these are applied and experimental oriented research. Basic research, which must happen into academic institution, is just 4% effort, and that's why the consumption on the basic research is just 4%. That is the reason that the stature of this nation into the technological developed nation is still a big dream for this country. It is not happening because the basic research is the engine which promotes, it's the burner which promotes the applied research and experimental research. So Indian scenario, just last two slides and we will sum up. India produced the most number of graduates worldwide with million of fresh graduates, out of which 2.6 million were from the STEM. So we have a good number of STEM graduates coming up every year. Indian natural proclivity for jugaad, that is a problem solving using the limited resources, aside, we also have a concentrated effort to encourage R&D investment. Jugaad is fine, frugal innovation is fine, but we have a very streamlined policy and investment in promoting R&D. India spent 0.7% of their GDP, that is 1.3 lakh crores, on doing research and development. And the projection is that by 2022, this should increase to 2%. And also the investment in education should increase from 4% to 6%. Within India, there are around 400 national laboratories, 400 R&D institutions in government sector, about 1,300 R&D institutions in industrial sector. 400,000 personnel are employed in R&D establishment. India's more than 300 universities and educational institutes produce around 450,000 S&T personnel every year. So if you see the infrastructure, the money is there, infrastructure is there. India's skill base is growing, More than 300 multinational companies have opened their R&D centers and laboratories in different sectors. So these multinational companies have come and they are utilizing this infrastructure and manpower for doing R&D. India is highly cost-effective R&D destination and also has a high-quality young workforce, as evidenced by major international companies investing in R&D hubs in India. Despite 9% increase in operating cost of R&D centers in India, it is still 25% cheaper than doing in China. So if we can capitalize this USP, we can grow our R&D capabilities by 10 to 15%. This is what is being portrayed now. So if this doesn't happen, if the R&D investment and the R&D encashing doesn't happen, in spite of all this, India's ambitious dream to become a developed nation by using science and technology by 2020 and rank among top 5 globally GDP nations and provide a world-class standard of living still remains our dream. So with this, I stop here and I am open to any kind of questions and discussions. And you have seen what is a landscape in a very short glimpse and also the challenges what we have in spite of our trained manpower, in spite of the money available, and in spite of the policy of increasing it to 2%, doubling it, more than doubling it in next 5 years. But the question is, who will be the takers for this? Multinationals all across the world have realized that India is a very economical destination for doing R&D, and that's why most of the R&D hubs are now coming to India and they are using this infrastructure. Thank you so much.
Thank you, sir. I'll just read out the few questions just come in the box, sir.
Of course.
What is the role, Mr. Sumant, he's asking, what is the role of 3D printing and AI in creating a paradigm shift in manufacturing process? And what is the ensuing social impact?
I will not take the technology specific question, talk on the R&D management aspect.
Okay, fine, sir.
What this particular technology is doing and how it is impacting is beyond the purview of this session.
Fine, sir. He's again asking us, are there any difference between open innovation and user innovation?
Open and?
User innovation.
Oh yeah, of course. So user innovations are generally done with the lead users. Apple follows a procedure of user innovation. So they have certain lead users. Even the software companies, when they release their alpha version of the software or the beta versions of the software, it is doing innovations with the lead users. That is a limited set of lead users attached to a company, whereas the open innovation is in the crowd. So that's more larger field of gathering the ideas and creating the solution to your problems.
Similarly, is again one more question, sir. He's asking, what is the task of management controller in the era of open innovation?
Yeah. So the R&D manager will become more a facilitator or a licensor, right? So he will be creating enabling environment, providing facilities, and providing a platform where the crowd, the open crowd, and the people who are going to pull the ideas of that come on that particular platform. So he is going to create that kind of policies, that kind of SOPs, that kind of procedures, that kind of design of a team. I've used a team called Jelly Team. So go into details of the Jelly Team. So creation of this cross-functional aggregation Jelly Team will be the responsibility of the R&D manager, rather than sitting on a table as a domain expert doing R&D.
So basically, so one more question is with respect to the DRDO, sir. Has DRDO adopted the open innovation or not, sir? If not, what are the reasons?
Who is the person asking this question? Is it from DRDO?
No, sir. He is an Air Force officer, Captain Dipesh Shaji.
Yeah, so Dipesh, DRDO still works in silos of ivory tower. We don't have a concept of open innovation, but my similar organization in US is called DARPA. The next version of submarine, that is a futuristic submarine, which is going to be launched by 2035, which DARPA and many Ivy League universities are working on. the design of this new submarine, the concept of a design of this new submarine has come from a 7-year-old student of a school in middle school in USA. So even the design of new submarines, futuristic submarines, they are open sourcing from the crowd. We don't think in this directions in India because we are a secret and a confidential organization, a closed organization.
Sir, does today's R&D professionals need be scientists but act as an integrator? It's more of an integrator.
There is no concept of a scientist or researcher today. We all are product engineers or facilitators, right? So we will create a multifunctional team. In that team, there can be few scientists from the basic areas. There can be few engineers from the different disciplines. There can be few entrepreneurs and few other experts. But as an R&D professional, I will be responsible for creating this team and either orchestrate that team or license that team to do a job instead of working with my own hands doing research. So that is what the R&D. So yesterday somebody asked me that Ramarao committee disintegrating DRDO. So the concept is disintegrate into R&D labs, TD labs, and lead system integrators lab. So my R&D professional will be part of lead system integrator. He will be orchestrating the job through TD labs and R&D labs and SNT labs. So SNT labs where the scientists will be there, TD labs where the product engineers will be there, and my R&D professional is a licensor and orchestrator who is coordinating the entire job. So this is the model he's talking about.
So how about race 2020? Is it moving in 6th generation in terms of AI?
What's the full form of race? I'm not being aware of that.
It is reliable artificial intelligence for social empowerment. The meeting which was launched yesterday by Prime Minister of India.
So this is a policy. This is a philosophy. It's not a program, right? So this philosophy will have so many players, stakeholders in that. So doing an R&D effort and a strategy and a policy, you should not mix with. Right. So how EI is a platform used for the social benefit. This is a kind of a program. And under that, there will be a number of projects in which we'll be doing R&D. And how the AI for the social benefit. Right. So it will have an implication in n number of industries. So when I will see the impact of AI on the society this is not an R&D study. This is a study of the strategy. So that's a different set of questions you're asking in the R&D paradigm.
I'll come to the last question, sir. Why Indian research organizations are not going for open source as the organization of Western countries do? How can we shift our R&D mindset?
I will not agree to that. Department of Science and Technology, Department of Biotechnology, Indian Space Agency, that is ISRO, Department of Atomic Energy, everyone has open innovation programs. It's only one or two